Hot water can freeze faster than cold water, which sounds like saying running late gets you there earlier, but physics is like, yeah, sometimes. This is the Mpemba effect, where hot water just speedruns freezing. Why? Evaporation steals heat like a tiny invisible thief, convection stirs things up like a chaotic soup, and dissolved gases bail out like they've seen the bill. The result? Under the right conditions, hot water beats cold in a race to become ice. Science didn't break. Reality is just weirder than your freezer manual. Hot water sometimes freezes faster than cold water, which sounds like something physics made up just to watch us argue. This phenomenon is called the Mpemba effect, named after a student who noticed it while making ice cream and basically got told, "That's impossible," until it turned out not impossible. The key phrase here is under certain conditions, because physics isn't completely unhinged, it's just selectively chaotic. When you start with hot water, several sneaky processes kick in at once. For one, hot water can evaporate faster, meaning some of it literally disappears into the air before it ever gets the chance to freeze. Less water left means less stuff that needs to turn into ice, which is like winning a race by quietly removing some of your luggage halfway through. But that's just one piece of the chaos puzzle. The rest involves temperature gradients, convection currents, dissolved gases, and a general sense that the universe enjoys plot twists. So while it's not guaranteed, don't go betting your freezer reputation on it, the Mpemba effect is a real, repeatable thing in specific setups. And it's a perfect example of physics looking at common sense and going, that's cute. One of the biggest reasons hot water can beat cold water to the frozen finish line is that it cheats by shrinking. When water is hot, its molecules are zooming around with way more energy, which makes it much easier for some of them to escape into the air as vapor. So while your cold water is just sitting there minding its business, your hot water is actively shedding mass, like it's on a crash diet. Less water means there's simply less material that needs to cool down and freeze. Imagine two people running a marathon, but one of them drops half their gear halfway through. Suddenly, they've got a much easier job. That's essentially what evaporation does. And it's not a tiny effect either under the right conditions. Enough water can evaporate to noticeably speed things up. Of course, this depends on things like airflow, container shape, and how humid your environment is, because evaporation loves drama. But the takeaway is simple. Hot water can lose part of itself before freezing even starts, which gives it a sneaky head start in the race to become ice. Hot water doesn't just sit there cooling politely, it stirs itself like it's trying to win a cooking show. This is thanks to convection, which is the movement of fluid caused by temperature differences. When water is hot, the warmer, less dense parts rise while cooler, denser parts sink, creating swirling currents inside the container. It's like a tiny weather system happening in your mug. These currents help move heat from the warmer parts of the water to the surface more efficiently, where it can escape into the surrounding air. Cold water, on the other hand, is much lazier. Without strong temperature differences, it doesn't circulate as much, so heat gets trapped in certain regions longer. Think of it like trying to cool down a crowded room. If everyone's moving around, opening doors, and waving fans, the heat escapes faster. If everyone just stands still, the room stays stuffy. Hot water basically has built-in chaos that helps it dump heat more effectively. So even though it starts hotter, it can sometimes cool at a surprisingly fast rate, because it's actively mixing itself, giving physics another chance to mess with your expectations. Here's a detail that sounds minor but turns out to be weirdly important. Hot water has fewer dissolved gases than cold water. When you heat water, gases like oxygen and nitrogen get kicked out because they'd rather not hang out in a high-energy environment. So hot water ends up being kind of degassed, which sounds like a spa treatment but is actually a subtle physics twist. These dissolved gases can interfere with how ice forms because they affect things like bubble formation and the structure of the liquid as it cools. With fewer gases, hot water can sometimes form a more orderly structure as it approaches freezing, making it easier for ice crystals to get started. Cold water, meanwhile, is still holding onto its dissolved gases like a hoarder, which can slightly disrupt the freezing process. It's not the biggest factor, but when combined with evaporation and convection, it adds another layer to the mystery. Basically, hot water is going into the freezing process with fewer microscopic distractions, and sometimes that gives it an edge. Physics didn't just bend the rules here, it added fine print. Water has a sneaky trick called supercooling, where it can drop below its normal freezing point without actually turning into ice yet, like it's procrastinating a phase change. Cold water is especially good at this. It can sit there below 0 degrees Celsius, still liquid, waiting for the perfect moment or disturbance to finally freeze. Hot water, weirdly enough, is often less prone to supercooling. Because it's been heated, it may have fewer impurities or nucleation sites behaving differently, which can make it start forming ice crystals sooner once it reaches the freezing point. So even if both samples cool down to the same temperature, the cold water might hesitate, while the hot water goes, "Nope, we're freezing now." It's like two people arriving at a party. One immediately goes inside, the other lingers awkwardly outside for 10 minutes. That hesitation can make a big difference in timing. So in some cases, hot water doesn't just catch up, it actually commits to freezing faster, while cold water is still overthinking it. And that's the Mpemba effect in a nutshell. Not one single cause, but a whole bunch of tiny physical quirks teaming up to make reality feel slightly broken.